Welcome to Pre-Calculus Notes 2-1, Polynomials and Factors, Essential Skill B1. In this set of notes, we're going to look at the definitions and properties associated with polynomials, and we're going to look at the factor theorem and the remainder theorem. First, every polynomial can be written as a product of its factors. A is a scaling factor, but the rest are factors, x minus r1, x minus r2, and so on. R1, R2, and R3 are the different roots of the polynomial. This is called factored form. If you know the roots of a polynomial, then writing it in factored form is easy. X minus root times x minus root times x minus root. To write this in standard polynomial form, we expand. When multiplying two polynomials that are more than binomials, I recommend the box method. Put the two polynomials as row and column headers, and then multiply to get each individual box. The nice thing about this method is that the like terms fall in the same diagonal. Recall from Algebra 2 that for any polynomial with rational coefficients, if we have imaginary or radical roots, they will come in conjugate pairs. Recall that conjugates are formed by changing the intermediate sign, the sign between the real and the imaginary component. Or between the rational and the irrational component. We can use this fact to solve problems. If we have a polynomial with rational coefficients, if we know two of the roots, we can find the polynomial in standard form. Notice that we will need to include a third root, since they come in conjugate pairs. If we forget, here's the problem. We start with x minus root times x minus root, but we've forgotten the conjugate root. Here's what happens. This is terrible. We have coefficients that are not rational. I told you we had rational coefficients. These are not even real. All of the polynomials we work with in this course will have rational coefficients. Now we'll do it the right way. If we have conjugates, it's important to multiply the conjugates together first, otherwise it gets very messy very fast. Note that this is a difference of squares pattern, making the multiplication very easy. Done. In our next example, our roots are going to be 2, 1 minus 3i, and its conjugate. When we write this out in factored form, we need to be careful that this is x minus root, regardless of the sign change when we use the conjugate. It's always x minus root. We put this in the parentheses to avoid sign errors. Note that I'm saying f of x equals. That's because the instructions ask for an equation, we must have an equal sign. When we multiply this out, we still multiply the two factors with complex conjugates first. Here's a trick. First, we're going to distribute the minus signs, and then we're going to regroup in a clever way. We have x minus 1 plus 3i, x minus 1 minus 3i. This is a difference of squares. So, using x minus 1 as the a in the difference of squares pattern, we get a squared minus b squared. To multiply this out, again, I recommend the box method. Now we collect the like terms, and we have our answer. Our next task is going to look at factoring. When we factor, we're going to use synthetic division a lot, so here's a quick refresher. When x minus 1 is the divisor, 1 is the root that we're testing. Now we add the coefficients. Notice that I've left 0 as placeholders for the x to the fourth and x to the first terms that are missing. The first number comes down, we multiply by 1, we add, and multiply. The last number becomes our remainder, and we build our quotient out of the numbers on the bottom. Our result of the division is a combination of the quotient and the remainder. Remember that in the result, we put the quotient over the divisor. One observation I'd like to make now is that if we take the numerator polynomial and plug 1 in for x, something interesting happens. We get the same number that was the remainder from the division. This is no coincidence. This is, in fact, the remainder theorem. The remainder theorem states that if we have polynomial p of x and we divide it by x minus c, the remainder will be the same as if we had plugged c in to the original polynomial function. In other words, if all we care about is the remainder, we can get the remainder by plugging in instead of using synthetic division. Here's a comparison of methods. First, with division. Our next example is going to show a case where the remainder theorem is much easier. I'm not even going to set up the division. That would take too long. There are too many missing exponents. The remainder theorem, though, says we can plug in. That's going to be much faster. Typically, the remainder theorem is easiest when we're dividing by x plus or minus 1. Our final topic is the factor theorem. This is what ties the remainder theorem to the actual factoring of polynomials. We know from simple multiplication that if one number is a factor of another number, then when it's divided into that number, the remainder will be 0. The same holds true for polynomials. You can see how this follows from the remainder theorem. Here's an example. We're going to divide a polynomial by x minus 3. The factor theorem states that if the polynomial divided by x minus c has remainder 0, then x minus c must be a factor. We can use this fact to write p of x in a partially factored form. P of x is equal to x minus 3 times the quotient we found. In our next set of notes, we're going to look at completing the factoring of polynomials. Thanks for watching.